I'm talking about what happens when an object feels a force. What happens when an object feels a force? A net force. What does happen? It'll accelerate, right? Does that sound familiar? Yeah. So we said that when an object feels a force, it causes that object to accelerate. That's an important thing. Maybe I should say a net force. Cause an object to accelerate. A force, you know, when we've been drawing forces on our free body diagrams, a force on an object always has to come from what? Another object, right? Do you remember that? We've been saying that over and over and over. So like when we draw our free body diagram, we say the force of the earth on the frog and the force of the floor on the frog. And you know what I'm saying? That stuff. So the other thing that I want to write down is that any force, oops, that was not a very nicely worded thing, must be caused by an object. And that's something we know. But today what we're going to do is to look more deeply at what that is. So last time, like in the last few days that we were together, you know, we rolled that bowling ball and we looked at what happened if you had an acceleration. We determined that when there was an acceleration, there was a net force, and when there wasn't, there wasn't. And if you remember, and I know it's been a little while, but if you remember, I lumped that statement of net force causes acceleration, no net force means that there is no acceleration. I called that, do you remember what I called that? Like the official name of that? Newton's first and second law, right? Now, at the very beginning of chapter 4, I told you to forget everything you knew about forces. So hopefully you've done that. But if you didn't listen to me when I told you to do that, you probably recall from some other time in science class that Newton doesn't just have 2 laws. How many laws is he famous for? 3. He's actually, truth be told, famous for many more than just 3. But they were like the 3 laws of Newton, right? Newton's 3 laws, okay? And we took Newton's first and second law and I put it as one thing. Today, it's nice that you're here today because today we are going to talk about Newton's third and most important law. Okay? I wish if I were in charge of the world, I do a lot of different things, but if I were in charge of the world, I would have called this number 1. Like, this is it. If you know this, you can do everything else that we need to do. Okay? This is the most important one. Why they relegated it to 3, I don't know. Seems kind of rude, right? Like, third, like, it seems, you know, like, the first one's going to be the most important, and the second, and the third, like, you may want to forget it or something. But we don't want to forget it. It's the very, very most important. Okay? And I'm going to tell you what it is, but I'm not going to tell you in words. I'm going to tell you as a story. And this story involves my very, very least favorite Winter Olympics sport. So if you think about the Winter Olympics, we had Winter Olympics, was it just recently or was that a while ago? No, I don't remember. Did it just happen? My least favorite Winter Olympic sport. Anybody want to give it a guess?
Curling?
No. In fact, every time I tell this story, the first person to guess says curling. And it breaks my heart because, in fact, curling is the best Winter Olympic sport. It is so, have you ever watched it? Like, it is so intense.
I like ice rink.
And they yell, and they use friction, and it's all really just physics. Curling is, in fact, the best Winter Olympic sport. Other guesses, Jake, I'm not going to call on you. Other guesses, what do you think? My least, was everybody going to guess curling if you all had your hands up? Curling is the best Winter Olympic sport. Guesses?
Skiing.
Skiing. I don't mind skiing. Like, it's fine. I mean, especially like ski jumping, that's kind of cool, right? Like, there's danger involved and like, yeah, projectile motion involved, and that's pretty cool. I mean, like, I'd take it or leave it. It's not my least favorite, though. Anybody else want to give it a shot? Give a guess?
Is it the
Cardling's least favorite.
sledding?
No, that's so cool! Man, like the luge?
Yeah,
Is it ice skating?
Kind of. So, I really like to watch figure skating. I think figure skating is fascinating. But there's a subsetting, no, I like that too. There's a subset of the figure skating kind of realm that I find to be particularly boring, okay? And I really have to make it clear that if any of you are future Olympians in this sport, I am not trying to diss your sport, okay? I can't figure skate. I can't ice skate the same way. Like I can go around very slowly and usually not fall on my butt. Like that's about as good as I am. But my least favorite Winter Olympic sport is ice dancing. Okay? Are you like an ice dancer? You're like looking at me like, okay. Oh man. Okay, so ice dancing. Have you guys seen ice dancing? Yeah? Like, so ice dancing is like figure skating, except they can't do any of the cool stuff. They don't do big jumps. It's always in partners, but they can't throw each other. Like, pairs figure skating, you know what I'm talking about? Like, one of them will like launch the other one across the ice, and whoosh! And it'll be so cool, right? Ice dancing, not so much. It's like the sappy sport, okay?
We won the gold in it.
That's lovely. Good for us. It's still sappy. You also have to know that, like, sappy movies, not my thing, right? Like, whenever we're watching a movie and there's like a love story, I always like, oh, and my husband's like, come on. I'm like, oh, like it's just so, like, come on. Where's the like stuff happening, right? Yeah, like I don't like the sappy stuff.
Michael Bay.
What was that?
I said Michael Bay. Hand explosions.
Yeah. Okay, so the thing about ice dancing that I don't like is that it, like I said, is really sappy. Every single ice dancing routine, every one, starts off, well, I would say 80% of them, 90% of them start off in the exact same way, okay? There are two ice dancers. Come here, will you be my partner? There, I suppose. They stand facing each other and they put their hands up like this, right? And they gaze into each other's eyes, and that's the part I'm like, oh my gosh, right? And then what happens after so they're standing here like this, the music hasn't started. The music starts, and what happens? What do? Push off. Push off. Right? And then a whole bunch of boring stuff. Thanks. I just need to think somebody to like be my partner there. Right? That's how pretty much all of them start. Okay? Now, there is a little bit of physics in there because as they're standing here like this, what's my velocity? Zero. I'm not moving. Would you all agree with that? Okay? At some point, my partner does what to me? Pushes, applies a force, and causes me to accelerate. Would you agree? So, I mean, that's kind of interesting, and that's why we care about it for the story. But really, it's like, whatever. Okay, so now let's put it in a little more context. So back in the day, I didn't know that the U.S. won ice dancing the gold. That's pretty cool. Good for them. Yay! Ice dancing. It's like I need a little, like, flag. I don't know. Anyway, yay, ice dancing. Back in the day when I was young, when I watched a lot of Olympics, the Russians were really, really good at ice dancing. Okay, so my story is going to be about two Russian ice dancers. We'll call them Alice and Boris, so that we have some names. Okay, so Alice is standing here, and Boris is standing here. Yes. Yes. And he is gazing down into her eyes. And she's gazing up into his eyes, and this is where I'm like, oh my gosh, this is so lame, right? And then the music starts, and their initial velocities are both what? Zero. Everybody good with that? Okay? And then the music starts, and Boris applies a force to Alice. Would you agree? And as a result of that force, where does Alice go? Backwards. Right? What happens to Boris?
moves backwards too.
A little bit.
He goes backwards, right? Because does he feel a force? He does. He feels a force from whom?
Alice.
From Alice, right? Does that make sense, right? Because Boris pushes on Alice in that direction. Alice pushes on Boris in that direction. So he's going to go that way. Are their motions the same?
No.
No. Why do you say no? Gut feeling? Hmm? Why do you say no? Why do you say they're not the same?
Boris has a larger mass.
Hey,
She's
that's,
making some
I think the Boris
assumptions,
is
isn't
incredible
she?
dude.
Right? We don't know.
But you
Now,
make him
the
a
reason.
Boris could be like 2 feet tall.
Right, and this is one of the points of this story, right? Is that we do make assumptions. Whenever you listen to a story, you make an assumption, right? You make assumptions all the time. Many people in this room probably made the assumption that Boris, perhaps because of his name, perhaps because I was going like this, assumed that he's a very large individual, whereas Alice is a very petite name, right? Okay, and so we may assume that Alice is very, very small. It may not be true, but for the purposes of the story, let's go with that assumption. Fair enough?
Okay.
For the purposes of the story, we're going to say that Alice is less massive than Boris. Now, let's draw some pictures here. I'm going to draw a picture of Alice, and I'm going to draw a picture of Boris, and I'd like you to draw the same pictures,
Favorite.
right?
Ice dancers.
Right?
The blue board.
And then I would like for you to draw a free body diagram of Alice just as the music is starting. So just as what is happening? Boris is pushing, right? And then I want you to draw a free body diagram of Boris. These are separate pictures, really. With the forces acting on Boris, just as the music is starting. Okay? I'm going to give you a minute to go ahead and draw those pictures. Once you've got some pictures, check with your neighbors and see if they agree with you. Then we'll put them all together. All right. So let's talk about Alice first. Can somebody raise your hand for me and tell me a force that you have drawn as part of the free body diagram for Alice? Maya, what you got?
I have an arrow going down that says the force of Earth on Alice.
Awesome. Do you guys agree with that? Sweet. What else you got? Go, yeah.
I have an arrow going out,
Uh-huh.
and it's force of Boris.
Like this?
Yeah.
Okay. Yep. Do you guys agree with that? Fantastic. And what else? Anything else? Go ahead.
The force of ice going up.
Force of ice. Absolutely. Now, before we move on, I just want to point out something that kind of goes without saying because you know this. But first of all, does this match with what everybody has? Yeah. What do you notice about all of the forces that are labeled here? What do you notice about them?
They're all on Alice.
They're all on Alice, right? That's important. They're all on Alice. Let's do Boris. What you got? Raise your hand if you can tell me something about Boris. Yeah.
First on Boris.
Would you? I didn't hear what you
Force
said.
of Earth, sorry.
That's okay. Did you say Firth? Does that going down?
Yeah.
Okay. That's all good. I just want to make sure that I wasn't making assumptions. Sometimes I do that, and I feel bad when I do that. All right. What else? What else? Go.
There's one going out where it's the force of Alice on Boris.
And what else you got? Something else? Is there another force drawn there? Sean?
Going up, the force of ice on Boris.
Okay. All right. Any issues or questions there? Does that sound okay? Okay. So, you'll also notice on the Boris picture that all the forces say on Boris. So just a nice reminder that a free body diagram is going to have all of the forces acting on how many objects? One object. I'm going to write that down. You might want to write that down just to remind yourself again. Okay? That a free body diagram has all the forces acting on one object. But we know that every force is an interaction between how many objects? Two, right? And that's important also. Every force is an interaction between two objects. Newton's third and most important law has to do with this part. The interaction between two objects. Okay? The force of Boris on Alice and the force of Alice on Boris. What do you notice about this set of forces? These two here. What pattern do you notice? Yeah?
They include both objects.
They include both objects, and what do you notice about the order of them?
They're, I don't know how to explain it, but like, for
Yeah.
Boris,
They're opposite. Yeah, is that okay?
Yeah.
He just looked at me and was like, I've got that word for you. Yeah. They're flipped, right? The labels are flipped. Okay? So you got the force of Alice on Boris. You got the force of Boris on Alice. Now, this is the important piece of the question. Well, there are a couple questions. First question, who pushes first?
Don't they push simultaneously?
No one has some more force going in their direction.
Who pushes first? Who pushes first? What did you say back there?
I thought they pushed simultaneously.
Why?
I just assumed.
It just seems like it makes sense.
Yeah.
Okay?
Well, wouldn't they both have to in order for both of them to move? Because if one pushes like before the other, that person will go back and they'll probably stay where they are.
Does that make sense? Like if Alice pushes on Boris before he pushes on her, then somebody's going to start moving first. Does that happen?
maybe.
Does that happen?
Yes.
In real life?
Yes.
If I push on you, can I push on her before she pushes on me?
Yes.
No.
You
Might be
can't.
able to get her going forward eventually.
You'll see a bigger chain. I mean, like she could
There might be a different what?
chain.
Change in what?
So
Change in velocity or a different acceleration. But who pushes first?
The guy with the larger mass. I don't know.
I want you to take your hand and push on your partner's hand. If you're in a trio, then you have to do it twice. Who pushes first? Push. Who pushes first? Push. Who pushes first?
Never get there first.
The person who's reacting.
It's like first and worst. I don't know how to explain it. I feel
All
bad.
right, come back to me, come back to me, come back to me. Way back at the beginning of our force conversation, we said that there were these four weird fundamental forces, right? But the force that you're applying to your partner is a what kind of force? It's contact force, right? So let's talk about, so the force actually happens when there's contact. So if you put your hand up and your partner puts their hand up, who touches whom first?
you can't
Whoever
tell.
put their hand up.
Nobody. Jesus, that's same time.
Ah, she touched me first! No, who touches who first?
Nobody.
Nobody.
Nobody! I'm touching you at the same time you're touching me, right? So you can use this to your advantage if you have siblings or people that pick on you a lot, or you pick on, or you want to be that tattletale whiny kid, right? Like if you have a younger sibling, they're like, he touched me first! Right? You know what I'm saying? Actually, Mom,
According to physics.
according to, you don't have to say that because it's just true. You don't have to like preface. No, actually, I touched him at the same time that he touched me, right? Yeah. Now, Now, it may have been that somebody else was instigating it, but who touches who first? The force happens what? Same time. Same time, okay? The forces, these forces, I'm going to say appear, but that's kind of an icky word, okay? But they come into being at exactly the same moment, okay? Who pushes longer?
Neither, because they have to be touching still.
As soon as they're not touching, then what? Then there's no force from this one or vice versa, right? Okay, so they start at exactly the same time, and they last. Okay? A force has to be an interaction between two objects. Alice pushes on Boris, and at the exact same moment, Boris pushes on Alice. At exactly the same moment and for exactly the same amount of time. And as soon as Boris lets go, Alice is letting go, right? It's the same thing. And the force is no longer. Okay? Now, this is the deeper question. Who pushes harder? Who pushes harder? I want you to think about that for just a minute. Does Alice push on Boris harder? Or does Boris push on Alice harder? Just think about that for just a second. I want you to write down something on your paper. Which do you think it is? Who pushes harder? Does Alice push harder on Boris? Or does Boris push harder on Alice? Write something down. Make some commitment. You can make that commitment in pencil. You don't have to write it down in pen. You can just write it on the side of your paper. It doesn't have to be a big statement. Have a conversation at your table. Who pushes harder? Is it Alice or is it Boris? All right. Mitch, what did you guys say at your table?
I said that Boris pushes harder, but it doesn't mean anything because...
What do you mean it doesn't? I mean, that's your opinion, right?
Yeah.
That means something. Don't sell yourself short. Come on now.
Well,
Did your table mates agree with you? Yeah? Okay, so both of you guys said Alice, and you guys both said, I don't do it, some like gender segregation there. What'd you guys say?
We all said Alice.
You all three said Alice. What'd you guys?
Smaller.
If she's okay, so we're gonna make that general assumption that Alice has less mass than Boris. Everybody okay with that? Okay. Alice is smaller than Boris in actuality. You say that Alice has to push harder. What did you guys say back here? Voting on Alice? What did you say over here? Alice?
Alice.
Alice. Wow. What did you guys say?
We said neither.
You said neither.
They're going to win.
The question was, who pushes harder, Alice or Boris?
Both.
You said neither. Like, what is that about?
Well, last time it was a trick question. It was neither. That's not like the only reason, but that's what I was thinking.
This Carly's got to be tricking us.
Well, it just like
Okay. So you have a reason for that, or you just like, we're like, psh.
no, like
Because we
we
can see it like
there
working
you go.
either way because like
Okay.
Alice,
I don't know.
Stay in one conversation here. What'd you say?
because either Alice could push Boris and he would go farther, or Boris could push off of Alice harder and then he would go further.
Okay, so let's talk about physically what happens here. So Alice is standing here, and Boris is standing here, right? And they push. What physically happens to Alice? Where does she go?
Backwards.
And what do you know about her final velocity after that acceleration?
Faster.
Right? She goes like that until either she is smart enough to move her feet or she hits the wall, one of the two, right? Like, she's going to go back really fast because we're making the assumption that Alice is very petite, okay? Then you've got Boris. Tell me about Boris's motion.
Goes backwards. Goes back a little bit. It's like,
He goes backwards, and we're assuming there's no friction.
yeah.
So that means that as soon as there is no force, he's going to move it at what? Constant velocity. So eventually he'd get to the wall, but he'll have lots of time to realize that because his final velocity is very what? Small or low or something like that, right? He's going very slowly.
Insignificant.
So, does everybody agree with that scenario? Okay. Can you tell me why you guys chose Alice back here?
Is that because Boris has a greater mass, so it takes more force to move?
We got to get it moving, right? Sure. But you guys disagreed, and you said that you thought Boris pushed harder. Why? Just because you're like solidarity, or what? Was there?
Yeah, well, he has more mass, so.
So he's stronger,
Yeah.
right? He's been lifting weights. I am Boris. I'm lifting weights. Yes, yes. And so, what can you do to that little Alice?
They're awesome.
Woo! There she goes, right? So Alice has to get that big guy to move, and Boris, my goodness, gets him to or gets her to move, like, right? And you guys are the obstinate children that are making statements that are not what I suggested. But tell me more about what you were thinking, Sean. You were there, kind of, and then I interrupted you, because that's what I did.
Oh, well, like, Boris would, like, have to be able to push harder by either him pushing or Alice pushing. And if one of them, yeah, whatever.
So you're advocating for Boris now?
No. We're just saying Boris, he has, like, a larger mass, so somehow he would have to be pushed harder. But that could either be done by him pushing harder or Alice pushing harder.
Is Boris pushing on Boris? Does that happen? No. Let me ask a question. What is different between Alice and Boris? What do we know for sure is different? We know their mass, right? We know that the mass of Boris is much larger than the mass of Alice, right? What else do you know based on the story? What do you know about their accelerations? Well, what do you know about their initial velocities?
They're not rushing anymore.
Both 0.
Initial velocity for Boris is equal to the initial velocity for Alice because it's what? 0. What do you know about the time that the force was applied for? The time is the same for both Alice and Boris, right? What do you know about the final velocities? Are they the same?
Alice is greater than Boris.
Right, their acceleration is different. And if we talk about, like, she's going, and he's going, right? So we know that his velocity is what? Compared to hers, I guess is what I mean.
Lower.
Bigger or smaller? Boris has a velocity that is
Boris will be slower.
smaller, right? So it's going to be less than. And using these things here, so if the initial velocities are the same, the times are the same. If the final velocities are different, you know that the accelerations have to be what?
They're different.
Different. Who's going to have a bigger acceleration?
Alice.
It's going to be like that, right? And if we're talking about the net force acting on Alice, or the net force acting on Boris, it's just that object's mass times that object's what?
Acceleration.
Acceleration. The force will be mass times acceleration. So we've got, in this story, a really big mass times an itty bitty acceleration, and a really little mass times a really big acceleration, Does it make sense that you can have one that's big and one that's little? Switch them, and in fact, they will be the same. Okay. The force of Alice on Boris has the same magnitude as the force of Boris on Alice. What's what? You were right. You were right. Good job. Are the directions going to be the same?
No.
No. What do you know about the directions of the forces? Look at your picture.
Opposite.
They're opposite in direction, right? So these two forces that come into being at exactly the same time and last exactly the same length of time, the forces will be equal in magnitude. What does magnitude mean? Size. And the forces will be opposite in direction. Okay? This is true for any, what we call Newton's third law pair. For any Newton's third law pair. So that's going to be any two forces where you've got Alice on Boris, Boris on Alice. Same objects, switching the order. Are you with me there? Is that okay? Okay. Same object switching the order. The forces will be equal in magnitude. The forces will be opposite in direction. And the objects that we label, I'm going to say only two objects involved. So it's f of b on A equals the negative of f of A on B. Okay? Are you okay with that so far? This is Newton's third law, right here. Even though I told you to completely forget what your elementary and middle school science teachers told you, I do need to address something about that right now. Oh my. Usually, when middle school and elementary school teachers teach you this, they say, for every action, have you heard this? There is an equal and opposite what? Okay. That is the last time I ever want you to say that word in this context. Okay? The prefix re means what? Again, right? Or after. That implies that if I push, she's going to push on me, but it's going to happen when? After. And does it happen after? No, it happens when?
Simultaneously.
Same moment. Are you with me there? Okay? This is what you need to know. Every time that a force exists, that's an interaction between two objects, there will be a force that's exactly the same size in the opposite direction, acting at exactly the same moment for exactly the same amount of time. Is that okay? Okay. All right. You're nodding your head saying yes, so now we're going to put that to the test and see if this actually works. All right. Is that a Newton's third law pair? Raise your hand if you say yes, yes it is. Raise your hand if you say no, no it's not.
Wow.
Okay. Why'd you say no?
For the Newton's third law, it should be like the opposite, in which they would counteract be like, there's the objects.
Mm-hmm.
So if they're like repelling each other, I guess there needs to be like one down and then the other one be an opposite way. Yeah, and if there were opposites in this one, there is no opposites the same way. So,
Can you tell me, what do you mean? You said there is no opposite. What do you mean by that?
like, okay, so there's no like opposite force that's not in a different direction.
Okay, so my argument is going to be this one is pushing up and this one's pushing down.
But like,
Those are opposites.
the Earth can't be
Say that louder.
the Earth can't be on top because
So this doesn't say Earth, is what you're saying?
I mean, okay.
I'm almost with you. I just want to make sure that I'm understanding what you're saying.
So,
You're doing a really good job. Keep going.
so in opposite ways, right? It
Uh-huh.
flips around
What's it?
the forces,
The forces.
and so if don't look at me.
No, you're doing a great job. Keep talking.
I'm getting there. Give me a
Yeah,
second.
you really are. Keep going. You're fine.
Okay, so the Earth always has the direction of down, right?
So the Earth pulling on the frog is always going to go down.
Yes.
Okay, keep talking.
And so if there were to be a flippage,
Okay.
the Earth would still be in the same direction, and so it would not be opposite.
Okay.
That's like the law.
Yeah. Okay, you're there. Right? So here's the thing. Not a trick question. A careful question. Are these, so I'm looking at this picture here, looking at my little checklist. Are those forces, the table on the frog and the Earth on the frog, are they equal in magnitude? Yeah, they are. How do you know that they're equal in magnitude?
It's not going up or down.
It's not accelerating, right? So we know that these forces are equal in magnitude. Okay. Are the forces opposite in direction? Yeah, they are. One's going up, one's going down, right? Are these forces talking about only two objects? No. How many objects are listed here? Three objects. Are you with me there? Okay. This is a big deal. You may want to draw this picture again. I know you have it drawn in your notes a million times, but the thing to point out about this picture, it's important. This is a really nice free body diagram of the frog, but there are no Newton's third law pairs in this picture. And I claim, and I want you to tell me why, my claim is that there will never be a Newton's third law pair in a free body diagram. Why? I'm going to claim that, but I want you to tell me why you think that's right. There will never, I think, be a third law pair on a free body diagram. Why?
Because Newton's third law pairs are pairs, so two objects, and free body diagrams are only one object.
It's all of the forces acting on one object. So this is going to say on the frog, this is going to say on the frog, and every time you talk about a third law pair, it's going to be like B on A on B. Are you with me there? Okay? So there will never, ever be a third law pair on a free body diagram. Don't let anybody trick you. Okay? Yeah?
So the ice skating one was actually two free body diagrams?
Correct. And I did say that, but you probably didn't catch it because we weren't really focused on that, right? Okay? So let's go back to that because that's actually going to lead us to the next thing. Okay? We had two separate free body diagrams. One for Alice and one for Boris. Does Alice accelerate? Yeah. Bing, right? There is a net force acting on Alice. Does Boris accelerate? Yeah. There's a net force on Boris. These two forces here are the third law pair. Okay? If you look at them together as one system, as one set, what's the net force acting in that green box? What's the net force acting in that green box? If we add up all the forces, where will it go?
0.
He says 0. What do you guys think? I don't ever trust Zach on the first try because, you know.
Either.
Yeah, they have to
Because then he
equal
learns all the
0.
options.
Yeah.
Because what?
Because then he learns all the options.
That's right, and then who
As soon as he
knows?
says,
How does Earth on Boris compare to ice on Boris?
Equal.
Those are equal and opposite. Is that a third law pair?
Yeah.
No.
No. Maybe. I don't know.
We're looking at a free body diagram. Is that a third law pair?
No.
Absolutely not, because you'll never what?
Have
Find
a
a
third
third
law
body
pair in
diagram.
a free body diagram.
Ever, ever, ever. How do these two compare? Opposite in magnitude equal in, or opposite in direction equal in magnitude? Are these a third law pair?
No.
No, they're not. But you know she's not accelerating up or down as a result, right? How does this one compare to this one?
Equal and opposite.
Equal in magnitude, opposite in direction. Are these a third law pair?
Yes.
Yes, they are. If I was going to draw a free body diagram of them together, the net force would be 0. Because this would be what we call an internal force, something inside. Okay? The reason that is nice is because when we draw the free body diagram for the frog, we don't have to draw the forces between all the molecules inside. We'd be here all day, right? That wouldn't be good. We'd have a little force going this way, a little force going this way, but it's a third law pair, so it doesn't matter. You with me there? Does that make sense? Okay. So it just depends on how you're looking at it. Are you okay so far? I'm going to throw one more thing at you before we go. Okay? This is all chapter 4. They don't go into it this deeply because I don't think they care that much. But I care. I'm going to tell you that I really, really like this law. Okay? I really like it. Probably you want to make sure you know something about it next time. Just saying. Okay? Just saying. In chapter 6, they introduce this brand new thing. You notice we skipped chapter 5. The reason we skipped chapter 5 is because chapter 4 and chapter 6 are the same. They introduced this brand new thing that is not a brand new thing. Let me tell you what they introduced to you. They say f of a on b is equal in magnitude and opposite in direction of f of
be on it.
b on a. And you say, by golly, I know that because I just did it in chapter 4, right? 35 seconds ago. Right? We're going to take this and we're just going to kind of break it down from where we started. If you know that the forces are the same, that means we can say mass times acceleration. Are you okay with that? So we're just working backwards from what we just did. So this is going to be the mass of, which one? A on B. So it's going to be the mass of, it's A or B. If I say the force of the earth on the frog, which mass do I want?
Frog.
Frog. So I'm going to do the mass of B times the acceleration of B. The claim is that that's equal to the mass of A times the acceleration of A. And there is a negative sign in there, right, to make sure that we know that the directions are opposite. Is that okay? And now I'm going to take it one step further, and I'm going to say, oh, what is acceleration? What is acceleration? And like the very first stuff we talked about. What does it mean to accelerate?
Change in velocity.
Changing velocity, right? Does that sound familiar? Change in velocity over a time. So now I'm going to write this out. It's going to be a little ugly for a second, but play with me for just a minute here. mb times is going to be the final velocity minus the initial velocity for object B divided by time is equal to the opposite of ma, velocity final, minus velocity initial for A divided by time. Is that okay? How do these times compare? They cancel out because they're the same, right? Because we're only going to push for the same amount of time, so I'm just going to get rid of them. See you later. We don't want you. And what this says is that there's this brand new thing. It's not brand new. It just has a new name. It's like when you go to the grocery store, the whatever store, to buy your toothpaste, and you're used to looking for the blue box, you know, and then they change it to a green box, and it says, same formula, new look. Do you remember what I'm talking? You know what I'm talking about? Or like this happens with your cereal or whatever. It's the same thing. It's just repackaged. Because this is really just Newton's third law, right? That's all we're starting with. They say, hey, look at this funny thing. We've got this m times, I'm going to write this as change in velocity. Silly thing. What are you doing? There we go. Is equal to ma times the change in velocity for A. Wow, it's a new thing! Shh, it's not. But they're going to take this thing that we're going to call mass times velocity, and they're going to give it a new name. Okay? The new name that they're going to give it is momentum. Okay? Momentum is just the product of an object's mass times its velocity at any moment. Momentum is marked with the letter, anybody want to give it a guess here? P. And it is a vector, mv. An object's momentum is the product of its mass times its velocity at a given moment. And the change in that momentum is the same on both sides. We're going to do a lab on Wednesday that will show you that that is really true. Thank you guys very much for your attention today. I will see you on Wednesday. Give the homework a shot. Read the book and you should be able to do it. Okay? Please recycle the pairs on your way out. There's a green recycle bin right there. Have a wonderful first day back. We'll see you Wednesday.